Hello. The purpose of this video is to review how to solve problems using the ideal gas law. As you know, the ideal gas law, PV equals nRT, tells us how four variables that can be used to describe properties of gases are related to each other. P represents the pressure exerted by the gas in atmospheres, V represents the volume occupied by the gas in liters, N represents the moles of the gas, R is the gas constant with the unit and quantity given there, and T is the temperature of the gas in Kelvin. Let's look at an example. In our first problem, we ask, what volume is occupied by 2.50 moles of neon at a pressure of 1.36 atmospheres and a temperature of 46 degrees Celsius? I call this a constant conditions problem because you have a sample of gas, nothing is changing, you're given values of three of the four variables in the ideal gas law, and you're simply trying to rearrange and solve for the fourth. So when it's a constant conditions problem, simply start by writing down the ideal gas law, PV equals nRT. Then, algebraically rearrange to isolate the variable you're trying to solve for. In this case, we're trying to find the volume, so we'll divide both sides by pressure. Pressure cancels, and we're left with volume equals nRT over P. We can now plug in 2.50 moles for N, the value of the gas constant with its corresponding unit. Temperature is given in degrees Celsius, but we know that we have to convert it to Kelvin first. So we'll do that in a separate operation by taking our 46 degrees Celsius and adding 273.15 to give us 319.15 Kelvin. However, the rule for rounding when you're adding is to round to the fewest number of decimal places, which is none, so this simply rounds to 319 Kelvin. So I'll plug that in for my temperature. Divide it all by the pressure of 1.36 atmospheres. Moles cancel moles, Kelvin cancels Kelvin, atmospheres cancels atmospheres, and I'm left with liters, which is what I expect for a volume. And my final volume is 48.1 liters. Let's do another example. What mass of methane gas, CH4, occupies a volume of 18.3 liters at a pressure of 782 millimeters of mercury and a temperature of 315 Kelvin? Well, mass doesn't appear in the ideal gas law, but moles do, and we know that if we can calculate the moles of gas, we can easily convert it to the mass by multiplying by the mole rate, molar mass. So again, we'll begin by writing down the ideal gas law, PV equals nRT. To solve for N, we'll divide both sides by RT, and we get N equals PV over RT. For my pressure, I'll plug in 782 millimeters of mercury. But wait, I can't use millimeters of mercury because R, the gas constant, has units of atmospheres in it. I have to convert from millimeters of mercury to atmospheres. I'll do that by simply embedding in it the conversion factor, 1 atmosphere over 760 millimeters of mercury. Volume is 18.3 liters. R 0.08206 liter atmospheres per mole Kelvin, and my temperature is 315 Kelvin. Check my units. Millimeters of mercury cancel millimeters of mercury, liters cancel liters, atmospheres cancel atmospheres, Kelvin cancel Kelvin, and I'm left with 1 over moles, which is exactly the same thing as moles. So that gives me a value of 0.72845 moles of CH4, which I'm not rounding because the problem's not done yet. To convert that into grams, I need to calculate the molar mass of methane, which I'll do separately. So I'll take the molar mass of carbon plus 4 times the molar mass of hydrogen to give me 16.04 grams per mole. So in the final step, I'll convert my moles of methane to grams by multiplying by the molar mass, 16.04 grams per mole. Moles cancel moles. And I end up with a final value of 11.7 grams of CH4 as my mass. Not too hard. Now, the other type of problem you'll see is what I like to call a changing conditions problem. And in this problem, you have a sample of gas under some initial conditions of pressure, volume, moles, and temperature, and then you change 1 or 2 of the variables, and you're asked to calculate the corresponding final value of one of the variables. Well, everything always starts with the ideal gas law. So I'll write down PV equals nRT. And I'll ask myself, of those things, what never changes? The only thing that never changes is R, so I'll isolate R. R equals PV over NT. I'll write this out for an initial set of conditions, but I know that no matter what changes, PV over NT will always be equal to R, so I can write out that expression for a second set of conditions, P2V2 over N2T2. So when you have a changing conditions problem, the first thing to do is simply write out P1V1 over N1T1 equals P2V2 over N2T2. Now, in these problems, one or two of the variables will be held constant, so we cancel any variable that's not changing, then rearrange to isolate the variable you're trying to solve for, and plug away. So in this problem, I'm given a certain number of moles of hydrogen gas that exerts a certain pressure. I want to know what pressure would be exerted by a different number of moles of hydrogen in the same container at the same temperature. So, since it's a changing conditions problem, I'll write P1V1 over N1T1 equals P2V2 over N2T2. Since it's the same container, that means the volume isn't changing. V1 is equal to V2, so I'll cancel those from the expression. If it's at the same temperature, that means the temperature is not changing. T1 is equal to T2, so I'll cancel those as well. And the ideal gas law simplifies to P1 over N1 equals P2 over N2. Let's go back and label our variables. 2.045 moles, I'm going to call it N1. 136.8 kilopascals, I'm going to call P1. What pressure would be exerted means I'm trying to find P2. And 5.714 moles of hydrogen will correspond to N2. So, to isolate P2, I'll begin by cross-multiplying, and I get P2 N1 equals P1 N2. To get P2 by itself, I'll divide both sides by N1. N1 cancels, and I have my rearranged expression, P2 equals P1 N2 over N1. Now I can plug in. My initial pressure is 136.8 kilopascals. My final number of moles is 5.714 moles. My initial moles were 2.045 moles. Moles cancel. And notice that you didn't have to convert kilopascals to atmospheres because you're not using the gas constant R. In these changing conditions problems, you can use whatever unit on volume and pressure you want as long as you're consistent. In this case, because P1 was given in kilopascals, that means our final value P2 will end up in kilopascals, and we get a value of 382.2 kilopascals. Not too bad. Well, that's it for today. Good luck.